Design cloud storage and sync systems similar to Google Drive, Dropbox, iCloud, etc. So what we'll be covering is to design a cloud storage and sync system that whatever we put, we store any file such as PDF, text file, video, image up to some certain limit that gets uploaded and stored somewhere, and it can also be synced to all our devices from which we are connected. Requirement gathering. As usual, we first try to gather all the requirements. Ability to upload any file, say PDF, text file, docs, images, videos, etc. So our system should be designed in such a way that it gives the ability to upload any type of file. Sync these files to my devices. So if a user has, let's say, two devices, Android, iOS, so all the files that the user is uploading should be synced. Download these, sync these files to my devices. So if a user is logged in from multiple devices, so all the files that are being uploaded from one device should be synced to other devices as well. Download these files, giving the ability to download these files, what have been uploaded. Support both small and large files, say up to 5 to 10 GB or so. We also need to support both small files, let's say a TXT file, a PDF, a 15-20 MB of image or so, and large files, let's say couple of MBs, couple of hundreds of MBs or GBs of video, up to 10 GB. System needs to be highly available. We need to make system highly available, even though we can compromise a little bit on the consistency that all the devices that we are logged into can eventually become consistent and sync everything of all the files which are being uploaded from one particular device or from multiple devices. Need to prevent data loss and make upload download of large files optimized. So this is a good enough requirement and essential for our system that we need to prevent data loss. Let's say if a file is uploaded from our device, we don't have to lose that file data. So we have to design our system in such a way and scale it in such a way that it primarily doesn't lose data of user. And then we have to look into optimizing upload and download of large files. We can't directly do upload and download of very large files, say 500 MB, 1 GB or so. Considering if the network breaks, we have to retry uploading and downloading of the whole file again. Hence, we have to see how to optimize that part of the flow. Scale this to support, say, 50 million total users and 10 million daily active users. So we have to scale up to a good enough scale of 10 million daily active users and 50 million total users, basically uploading and downloading files, and all these users having multiple devices connected and need to bring their devices in sync with what has been uploaded from a certain device in sync to all the other devices which are connected to the system. Considering all these requirements, let's try to see what sort of back of envelope estimations we can do. Say on Google Drive or Dropbox, etc., our writes are also equally high as reads, as users are uploading huge amounts of data. And this makes sense because here we are uploading data, so our writes will also be quite as large as our reads. Each user upload has 10 GB of storage available to them. So while doing back of envelope estimation, let's restrict a little bit that each user has 10 GB of storage available to them. We had 50 million total users on our system. We have to scale up to that level. So 50 million total users, considering each user will be given 10 GB of storage available to them. So that would become 50 million times 10 GB. Million times GB would become 1 petabyte, and then 50 times 10 becomes 500 petabyte of storage would be required. Very high amount of storage seems to be required. So we will try to segregate our metadata of file and the actual file data and handle plus store them differently. Now, as we can see, we require very high amount of storage. So what we will do is to optimize a little bit on things and to segregate things, we will try to store the metadata of our files differently and the actual file, the raw file itself, a little bit differently, and also handle them differently as well. Now we have 10 million daily active users, and say each user makes 5 queries a day on an average. So QPS, which is queries per second, would be 10 million times 5, because we had 10 million daily active users. We need to scale our system to that level. 5 queries per day. So 50 million queries per day. And then if we divide it by 24 hours per day, and then 3600 to make it towards second. So we'll get around 600 queries per second. We have to scale our system up to that level. These good number of queries are writing data to our storage system. As our system is storing the files, which can be TXT, PDF, images, videos, etc. So these will be write queries like uploading all this data to our storage system. So we need to consider a storage system that scales well on good amount of writes to it. So we need to consider a storage system that can handle very high write throughput, as we have very good amount of writes, as we saw 600 QPS. As we just discussed above, we will be handling the metadata a little bit differently than the actual file data. So metadata like file name, file ID, creation or updation timestamps, updating a file, right? When the time it was updated, when the file it was uploaded at the first time. So creation, updation timestamps, what's the format of the file, what is the size of the file, etc. So all this metadata, we can pick up maybe Cassandra, DynamoDB, Bigtable, etc. We can consider this for storage of metadata. This scales well with high write throughput and is based upon LSM trees and SS tables concept, which uses balanced binary search tree and asynchronously flushes data to SS tables, and also performs well with key lookups and range queries using sparse index and Bloom filter concepts. File data. This can be stored on blob storage, say AWS S3 or Google Cloud Storage, etc. There it can be stored directly irrespective of its file type. So you can store metadata of the file a little bit differently than how the actual file data will be stored. Components we need. So we would require, as of now, we can see we might require API servers, then we require a metadata DB to store the metadata, and blob storage, say S3, to store raw file data. So we can see we require 3 components for now. Let's try to see the flow of upload files. Storage on S3, we can think of it as, let's say we have an S3 bucket defined or created. Then it might have a directory where each user has its own directory. So let's say XYZ user has its own directory under it. ABC user has its own directory under that. An XYZ user can have further segregation of folder structures such as images, docs, videos, etc. And then the images folder can have the images data in it, such as image1.png, image2.png, and so on. Similarly for docs, similarly for videos. Similarly, other users can have similar structure inside that as well. As earlier discussed, we can let our API servers upload the files to S3 bucket, which is our cloud storage taken in this case, as our system can have all roles and policies required to interact with S3. So what we can do is we can have our system consisting of all the roles and policies which are required to interact with S3, such as having put object action, get object action, delete object, and so on a S3 bucket. And then let our API servers take up the file. API servers take the file data plus metadata, write the metadata to the metadata DB, for which our case we are using, let's say, DynamoDB, Bigtable, etc. And then take the file data and upload it to S3. But this approach isn't scalable. Good way is to let clients or users upload data to S3 bucket directly via a pre-signed URL, which our API servers can fetch from cloud storage and provide back to us. This approach is fine that the API server takes care of uploading the actual file data and writing the metadata to the metadata DB, but this isn't scalable with this heavy queries per second, and considering that we can upload large files as well, this can choke our API servers. So the good approach would be that the API server would get something from the cloud storage, which is a pre-signed URL, having some expiry attached to that, and provide back to the user, and the user can directly upload the stuff via this pre-signed URL directly to the cloud storage, say S3 in our case. So if you check this diagram, what I just explained, that the users would interact with the API server. The API server would ask the cloud storage, considering our API servers will have, our system will have all the necessary roles, policies, permissions, everything attached to that. It will interact with the S3 bucket. It will ask for a pre-signed URL. This pre-signed URL is provided back to the user. Then the user uploads securely directly to the cloud storage. So a pre-signed URL which our API servers can fetch from cloud storage and provide to the users or the client, and let our API servers handle the writing of the metadata stuff to the metadata DB. So as I just explained, so these are the users. It will call the API servers. The request would go via the load balancer and API gateway. The API servers would then call the cloud storage, say S3, would ask for a pre-signed URL. This is returned back to the user, and the user can upload data directly to the cloud storage via the pre-signed URL. While asking for the pre-signed URL, API servers can also store metadata of the files which the user wants to upload to the metadata DB. API servers would be writing that to the metadata DB as well. So while users asking the API servers that they want to upload some data to the cloud storage, they would give out some information about the file which they want to upload, and that sort of information, that sort of metadata of that file would be written by the API servers to the metadata DB. We can store the metadata of a file which we want to upload. So client can tell API servers about file it wants to store to the cloud storage. API server will make an entry to the metadata DB with, say, a status field, started or open, and in parallel request cloud storage to provide a pre-signed URL. This will be returned back in response back to the client or the user. Client will upload similar file to the pre-signed URL, and once that is done, it can send an API call telling about completion of the upload. API servers will then mark the status as, say, completed or uploaded. So this is the flow which we are discussing, is how the metadata would be written by the API servers to the metadata DB, and how our actual file data will be uploaded to the cloud storage. So if you see, writing of the metadata is taken care of by the API servers, and the uploading of the actual file data is being taken care by the users itself via or using a pre-signed URL. The status thing we'll try to understand a little bit more in depth, why we wanted this status field of started open or then marking status as completed or uploaded, once we discuss the DB schema part of it. We can have another way to deal this. Now you might be thinking that firstly, while the client wants to upload the metadata or while the client wants to upload a file to the cloud storage, it provides all the file related information to the API servers. So similar to that, it can fetch a pre-signed URL and also write that stuff to metadata, keeping the status field as started or open, because the client hasn't yet uploaded the data yet, the files yet. Then the client will be using the pre-signed URL to upload all the data, and then send again an API call, will make an API call telling about the completion of the upload, so that the API servers, the entry that they made, they can mark the status as, say, uploaded or completed. So this seems like couple of calls to write metadata to the metadata DB, and then another call to update about its status. This is a fine enough way, but we can have another way to deal with this. This can be done via S3 events. Once API servers gives out pre-signed URL to the client uploads file to the cloud storage. Then rather than client sending a completion event to the API servers about the completion of the upload and API servers updating the status, S3 will emit, say, object created event to SQS, and we can have our workers which consume from SQS and store all metadata to metadata DB. So this sort of flow of sending out object created event to SQS and then consuming from it that event and then extracting out that event payload and writing that out to the metadata DB has already been discussed in one of my previous videos in detail. Check out the link above. Now let's deep dive a little bit into the DB schema, what things we are planning to store as part of the metadata DB. We will be discussing and majorly focusing on the metadata DB. I'm ignoring user table as that is quite common and also discussed a lot in other videos. For the metadata DB, we can think of as having a file name, cloud storage bucket, URL reference to refer cloud storage, say S3, user ID, ID of the user which uploaded these files, created at, when the file was first uploaded, updated at, if the file content is updated, so we update this field with a newer timestamp, and this will be helpful and discussed more detail in the syncing of data. If a client has updated the file at one of its devices, so syncing the data on other devices and also syncing the same data remotely. Version to mark the version of the file. Then there is status, open or say uploaded, which we just discussed above. Then you can have file format, size, and couple of other fields. And then another important field is checksum of file data to have checksum validation. So this will deep dive later in this video. Checksum is to validate if the file has been updated or not. So checksum changes based on that. So we need that as well to store. To optimize on the upload files, say our file can be 1 GB or so, we can have resumable uploads for Google Cloud Storage and multi-part uploads for S3. So to optimize things while uploading a certain file, uploading large files, we can have multi-part upload or resumable uploads so that if network breaks in between or some error occurs, we don't have to upload the whole file again. This uploads files in chunks, and the chunks are uploaded and managed independently. So if a part of a file fails, if a chunk fails, it can be re-uploaded again rather than doing it for the overall file. And that also makes a lot of sense and optimizes our upload process. Already discussed in my video sharing platform videos, a lot more in depth, how multi-part upload for S3 can help with this, optimizing this upload flow for large files. How large files would be brought into chunks and how we can take care of those chunks, we'll discuss a little bit more in depth when we discuss in this video about sync system. Before that, let's look into download files. Similar to upload files, we can have download files process. Clients will let API servers know which files to download. API servers fetches metadata of all those files from metadata DB, and clients call directly the URL references to download data from cloud storage, say S3, Google Cloud Storage, etc. So here what we are discussing is that the clients can call API servers, which will eventually fetch the metadata from metadata DB, what all files need to be downloaded, which have been uploaded by another system, another device, and then this client can call the URL references, use them to download it from the cloud storage, say S3. Our system gets highly available now considering cloud storage providers, say S3, have data replication, both same region and cross region as well. So you can configure for cross region as well, and globally they have very high number of data centers present. So our system being highly available is good enough by opting for these cloud storage providers, let's say S3, because they give out same region replication and the data gets replicated to other data centers as well, and also cross region as well. So we can configure that. So data loss is prevented by this. Let's deep dive into sync files across multiple devices. So let's say if a user has two devices, for example, a phone and an iPad. So if a user is uploading files from his or her phone, they want to have similar files synced to their iPad as well. To handle this feature, we need a client app installed on our system, say Google Drive or Dropbox client. So think of it as like your device needs a client app installed which will take care of this syncing process across multiple devices. So if you check Google Drive or Dropbox, they will have their client app installed on your device, similar to I mentioned in the screenshot. It will reserve your local storage to keep your uploaded downloaded files, keep your client app in sync with remote storage. So what these client apps will do, it will reserve some local storage on your device and will keep in sync from that local storage. If you have added some files, will keep it in sync with the remote storage or cloud storage. Now, if you try to observe, we have two scenarios which we might have to consider over here. That our local files got changed. We have, let's say, created a new file and put it in this client app local storage or directory, or we have updated a file which is already present, deleted, and that sort of stuff. So local files have changed on a certain device's local storage. And then the second flow is that remotely files have changed. So this user has changed or updated the files from the other device, and then they have been uploaded to the remote storage. Now files on the remote storage have changed. Now all the other devices need to get in sync with the remote storage. So with the local files change scenario, we push it to remote storage so other devices can sync them on their local storages, right? So let's say we have this device X and this device Y, and this is our remote storage. So if something got changed over here, it will update that to the remote storage, and this device will get the updated changes from the remote storage and bring out similar changes to its local storage. So something similar to that. And the other flow, so this can happen, let's say something changed on device X local storage. So those files will be uploaded and updated on the remote storage. And then for the device Y, to bring its local storage in sync with the remote storage, for it, it will have to consider the second scenario, pull files from remote storage and update local storage of this device. Device, Y device, right? Now, a question can come up that who will watch for the local changes? Let's say I made update to some file data, created a new file, deleted a new file. Let's say I had a txt file, added some content to that. So who will watch for these local changes and update them to the remote storage? Our client app implements OS level events to get notified about changes being done in a certain directory, which our client app has reserved. And this directory will be pointed to the local storage, as I just mentioned, which is being used by our client app. So it will implement these OS level events to notify the client app about any changes being made to this certain marked directory being used for local storage. For Windows, we can get directory change events such as file created, updated, deleted, etc. Similar events we can get in Mac OS as well, as we have FS events to be implemented for that. These events will be about which file got changed, created, updated, deleted, etc., all of that, and not about what inside the file changed. So let's say you have a file 1.txt and you updated some content into it. So it will let the client app know that file 1.txt got updated, but it will not let it know what got updated inside it. So we need to handle that as well. Now on a very simple level, we can see which file got updated on local storage, which part is sorted for us, and simply upload that file again to cloud storage and update in the metadata DB using our upload file flow, which we just discussed and deep dived above. So let's say if our client app gets the event that a certain file got updated, we can pick the overall file and use the upload file flow to get it updated in the metadata DB and also on the re-uploaded on the cloud storage CS3. Similarly, after a certain interval, say a minute or so, a client app can ping our API servers to ask about metadata changes since it made its last sync. And if new changes are present, we use download flow to download and replace download new files or replace existing files on this device local storage, right? So we can have a certain interval, let's say a minute or couple of minutes or so, after which it will trigger this syncing process of invoking the API servers, making a call. API servers will let the client app know about the metadata changes that are present since this certain device made its last sync call. And then if there are new changes, so this device will go, go via the download flow. So this device will use the download flow to download all these changes, newly changes that are present in the metadata, and get down and download new or replace the existing files from the remote storage on this particular device's local storage. Few things we might have to consider over here with this very simplistic flow, that how our client will know about to replace existing file or not. Second is, what if we have changed our file locally and it also got updated remotely as well, right? So first is that how we will know from the metadata DB that, let's say we had file 1.txt and the file 1.txt metadata now present in the metadata DB has been updated. And then what if we are also updating currently file 1.txt with some newer content adding to it, and then the file metadata present in our metadata DB remotely is also updated? So how we handle these two scenarios? These things can be handled by maintaining a local metadata DB, storing metadata about files similar to what it did with our metadata DB. So what will happen is, we can think of that our client app can also have a local metadata DB consisting of the file metadata it is having in its local storage. It can similarly have file ID, file name, format, size, then again created at if new file has been added to the local storage of the device, updated at if the file is being updated, path where it's added in that local storage, certain marked directory, then version of it, and then the checksum. So here version and checksum are quite important fields to have. As we discussed above as well, checksum of a file changes even if 1 byte of a file changes. So checksum, what we'll do is, let's see it from an example, what we mean by checksum of a file. So let's say I have a file 1.txt which has hello world in it, and let's assume its checksum comes out to be ABC123. Now we update file. Even if we update 1 byte of this file, let's say I did capital H to small h and rest kept the whole file same, so the checksum will change, and let's say it changes to XYZ235. What it does is read file as a sequence of bytes and feed it to a hashing algorithm, say SHA-256, to generate a hash value. This checksum is also pushed to the metadata DB during upload of the files, right? So checksum is computed as that it reads the whole file, take the sequence of bytes and feed it to a hashing algorithm to generate a hash value. And this checksum value is also stored in the metadata DB, both locally and remotely. A client app on syncing data, hitting the API servers to get all metadata. It will compare version and checksum of the file present locally and remotely. Say if local version is v1 and checksum is, for example, cs1 in the local metadata, and on remote, its version becomes v2 and checksum is cs2. So our client, it will download the updated file and replace it locally. Make sense? Then also update local metadata DB to v2 version and cs2 what was present remotely, and as that was more recent. Now another scenario, if our local file is also being changed currently, say local metadata DB has v1 version and checksum cs1. We are currently making some changes to this file. So these local changes makes it say version v2 and checksum cs2, but remotely it is present as version v3 and cs3 that already has been updated by another device. It will consider as a conflict and give out maybe file1 v2.txt and file1 v3.txt, keeping say both on our local storage. So it will pull the remote changes, the file changes which are now at a version v3 with a checksum value of cs3, and our ongoing local changes which are now at a version v2 and with a checksum of cs2, and then create a conflicting case here and give out double files for us, and then it is up to us to decide which to keep and which to delete and which to drop and that sort of stuff. Now this approach seems fine, but one thing is that it's an overkill to download the whole files even for minimal changes in it. And that totally makes sense, as we saw with our simple flow, that if our client app detects any changes on the files on our local storage, the directory that has been marked, it will go ahead and upload them, the actual files, data, and the metadata remotely, both to the metadata DB and our cloud storage, say S3. And similarly for syncing, downloading that from remotely to the local storage. So in the simple flow, we discussed that we will upload and download the overall file, even though there has been minimal changes done in it by comparing the versions and the checksums. And this to be done by all clients to keep local storage in sync with remote. Now this is fine, but it seems an overkill of uploading and downloading the whole file and might hamper our system for large files. So to optimize this, we can use the concept of delta sync, and this is what Dropbox also uses behind the scenes. This involves chunking of large files into smaller chunks. And then these chunks are uploaded, downloaded, managed, etc. over local and remote storage. So delta sync means that first our client app needs to break down our large file into chunks via chunking process, and then upload, download, and manage out these chunks to bring systems in sync, both on local storage and on remote storage, say cloud storage, say S3, and our metadata DB as well. With this, we need to just upload and download that particular chunk which got newly created, updated, deleted, etc. So that chunk that got updated, we need to only upload, download, and manage that. Let's say we were using DynamoDB, Bigtable, etc. What we did for files, similarly, we can do for chunks, and we can have that structure in our metadata table itself. A file field having list of chunk fields. So let's say a file, we have say file 1.txt, which is made up of say chunk 1, chunk 2, chunk 3, and so on. So all made out of all of these chunks. So these can be stored along with our file metadata fields. Similarly for these chunks as well, that these chunks can have some ID or some sequence, then status about these chunks that they have been uploaded correctly or not. So uploaded fully or not, similar to what we did for file, marking a status as open or active and then uploaded or completed. Similarly, we can do for chunks. Then URL reference of these chunks on cloud storage say S3. Then checksum of these particular chunks created at, updated at, and similarly couple of other fields for each of these chunks. Similarly, on our local metadata DB as well, we can have similar schema. So our cloud storage say S3 will store chunks rather than overall files. Now, as we are uploading, downloading, and managing these chunks, it is best that our cloud storage S3 will now store these chunks rather than the original overall file. As we saw above about that bucket, how it would look like. So let's say we have my bucket, and into it we had a couple of directories, let's say user1, user2, and so on for each of the user. And then inside the user, we had subfolders, images, videos, docs, etc., proper segregation. Then inside image, we can have for image 1, chunk 1, chunk 2, chunk 3, and so on, what makes up that image. Now, this is where delta sync comes into play. We can then do delta sync to see what files got changed, and within that, which particular chunks got changed. So rather than uploading and downloading the overall file with just a couple of things getting changed in that particular file, now with delta sync, we can see from the metadata which files metadata have been updated, and then within that file, which particular chunks data has been updated. Then by comparing versions and fingerprints, which is nothing but the checksum of individual chunks, and then only upload, download those chunks. So our client app said Dropbox, we have this file.pdf. Let's say it will have chunks as hash A, fingerprint, hash B, fingerprint, or checksum, hash C, and so on for each of these chunks. In our local metadata DB, similar schema we can have. We will have a file name, say file.pdf. We will have size, say 100 MB or something, then the format of it. And then we can have chunks. So let's say it is in bytes, say it is as 100, just supposing. So the chunks will have information about all the chunks that make up this file.pdf. So this will have info about all chunks. For example, 3 chunks make up this file.pdf. So it will have sequence 001, 002, 003 to know about in which sequence to play out these chunks. Then it's fingerprint or hash values or checksum values, version, and that sort of stuff. And then the size, let's say this will have 30, this will have 40, this will have 30. So it adds up and makes it as total size 100, which has been defined at the file name schema level. Now this would act as a blueprint for reconstruction of files from its chunks. Client app will concatenate all chunk blocks sequentially to restore the original file. So on our local storage, local metadata DB, we have information about all these chunks, and then these chunks are being stored on our local storage, the directory that has been marked. Then our client app can play out these chunks sequentially to form and restore the original file from that. We can also have a reconciliation process, say after a couple of hours or after a day or week or so, to check and compare a local metadata DB and storage with remote metadata DB and storage and get everything in sync on all the devices. So we are managing out chunks and all this file metadata, chunks metadata, and all that sort of stuff on our local metadata DB and our local storage on all the devices. And then we need to bring out in sync all these devices by doing delta sync with the remote storage and remotely metadata DB. But still, problems could happen, things can go out of sync. That is why we have reconciliation process. For example, it runs after a day or so, which checks and tries to bring the overall system in sync, all our devices on both local metadata DB and storage, and also with the remotely metadata DB and storage. So on a high level, what will be the design of this overall system? Let's try to review it once, what we have gathered till now. So let's say we have this user X. It has a client app installed. Now this user X on this certain device X, there are a couple of things going on. A client app has been installed. It has local metadata DB, as we discussed, and then has a directory as local storage. This is local storage and store chunks data, and they can be reconstructed to form the original file. This user X, the client app, will make the call and go via load balancer in API gateway. Our API gateway can be responsible for handling all the auth mechanism, rate limiting, and that sort of stuff. Will hit the file service. File service, as we discussed in the very beginning, will write metadata to the metadata DB about that file and about those chunks. And then also get pre-signed URL for the client app. This is then returned back to the user. And then the client app can upload those chunks via the pre-signed URL to the cloud storage, say S3. And similar thing can be used for download flow as well. So our client app is doing a couple of things over here. It is taking care of the chunking process. Then it is also responsible for doing delta sync by calling our sync service over here, uploading, downloading chunks data from cloud storage, etc. So client app is responsible for a couple of things for the chunking process, managing things on the local metadata DB and our local directory, and also uploading, downloading chunks data during delta sync. Now this metadata DB, this stores all info about files and their chunks as well. And then this sync service can be responsible of fetching the data from the using file service to fetch the metadata about the file and its chunks from the metadata DB, and then returning back to the client app.